Hello, everyone. Today's talk is going to be about DeepCrime. It's a mutation testing framework for deep learning systems that is based on real false. So, as we all know by now, that DL systems have become very widespread, and they're often used for the tasks where a failure can lead to quite great consequences, and ensuring a proper testing of these systems becomes more and more important. Mutation testing is a technique that's widely used in traditional software, and it's used to evaluate the quality of the test suite. And the hypothesis of the mutation testing is that if existing test suite can successfully expose artificial faults that were seeded in the program, it would also do good with exposing the real faults that can affect the software. So we have some program which we want to test, and we generate a number of mutants of this program by seeding some artificial faults. And that's usually syntactic faults, such as changing minus to plus sign, multiplication to division, and etc. So then we have some test suite that we want to evaluate, and what we do is we execute this test suite against the set of created mutants, and if all of the mutants were killed or exposed, and by that we mean that the test suite failed, like at least one test failed on a mutant, it means that the test suite was successful in exposing it. The mutant gets killed. So we want to check if not all of the mutants are killed by the test suite, so some of them survived. We get the intuition that we need to improve our test suite, because we know that we tested it on a faulty model, on a faulty system, and it passed. So it wasn't able to find the fault in our system. But if all of the mutants are killed, we can finish the testing process. So in traditional software, faults are usually in the software. So we have a developer writes some code, and if the software misbehaves, we get the intuition that most probably we have some fault somewhere in the code. In DL faults, the notion of a fault is a bit more complex. So we have a developer that also writes some code, but we also have some training data that was collected previously, and we also have selected a model architecture with all the optimizers, loss functions, and a big number of different hyperparameters. So when our DL model misbehaves, we cannot be sure that the source of the fault is in the code. It can be also in the improper data or in wrongly selected hyperparameters. So it makes the fault here a bit more tricky. And if we want to adapt mutation testing to DL systems, we cannot really use traditional syntactic faults that are applied to the software code, because it's not very realistic. Also, there exists a number of works that try to adopt the mutation testing to DL models, but their principle is in taking an older trained DL model, and when we train the model, we get some weights that were trained, and that help the model to predict make the prediction on the new data. And what these approaches do is they take these weights of an already trained model, they apply some random perturbations, and they say that this is the mutated model. But also, it's not very realistic. It's not like the many developers train a model and then take and do something bad to the weights and break it in some ways. So the goal of our work was to create mutation operators that are more realistic and that are based to real faults that affect DL models. So, and that would be mutating the training data, mutating the model architecture, or the source code before the training was done. So we can reflect a more realistic scenario for the fault induction. But what are the real faults in deep learning systems? To learn this, we went to the couple of sources, and the first of them is the taxonomy of real faults in deep learning systems. And this work I actually presented on the previous seminar. So we did this work when we analyzed the unstructured repositories of fault reports such as GitHub commits and fixes and Stack Overflow, and we did also interviews with developers. And we get a high number of artifacts, and we were able to construct a comprehensive taxonomy of real, false, and deep learning systems, which was later validated through the survey with developers. So by analyzing it, we were able to propose 27 mutation operators. And then we decided to complement this analysis by analyzing two other works that's focus on false and deep learning systems and frameworks. And we were able to get 8 more operators. So by the manual analysis of almost 800 issues, we were able to propose 35 mutation operators. And here you can see those operators divided in groups by the area of applications. So there are operators that can affect the training data, such as removing portion of training data or hyperparameters, or changing the activation of the less function. And we implemented 24 of these operators in a tool that we call DeepCrime. So what's important to know that almost all of the mutation operators in DeepCrime are parameterized. So what it means that if an operator has a parameter, by changing the value of this parameter, we can create different configurations of this operator and thus we create different mutants. So if we see an example, for example, we have the operator that removes a part of the training data. The parameter of this operator is the percentage of the removed data. So we can remove from 0 to 99% of the data, let's say, because ideally we want something to be left to train the model. And not all of the configurations are equal. So it means that we can create mutants and the configuration by applying some configurations of the operators that are very easy to be exposed. For example, if we delete 99% of the training data, most probably if we have an adequate test set, it will expose that the model is not trained enough. So, or if we delete just a very, very tiny percent of the data, probably a test set may not be able to find the difference between the model trained on the full test set and the reduced one. So what we want to do is to find the interesting configuration of the operator, which is not very easy to kill, but and also is not unkillable at all. So it could be useful to evaluate different test sets that we have. So for this, we apply binary search in the parameter space of the operator. So for example, we know that we can kill 99 configuration of the 99% of data deletion. Then we just check if we can kill almost 50% of training data deletion. Let's say that we could do it. Then we want to explore a less aggressive operator. Let's say something in the middle between 0 and 50%. We see that we cannot, our test set cannot expose this mutation. We move to the right half of the range and so on until we reach some point and some precision that we set to the tool, and we say, okay, this is the configuration of the operator that we can kill, but which is not very easy to kill, because if we try to reduce this parameter, we cannot kill the operator. Then we have different other operators that are list-based. For example, if we want to mutate a model by changing the optimization function, we in Keras and TensorFlow we have different options such as sizing gradient descent or other delta or other ones. So here the configuration would be changing different optimizer. Or we can have a user-specified parameter ranges, such as changing the batch size. We can manually say to the tool which configuration we want to use. So, but when we say that the mutant is killed in deep learning, what do we mean? Because in a traditional software, we have a test, and we say that the test was able to kill the mutant if it fails on this mutant. But in deep learning, we know that by having a model and retraining it a number of times, we can get a slightly different performance, and different instances of the trained model can behave differently on the same input. To mitigate this, we adopt the notion of mutation killing that was proposed earlier by my colleagues Paula and Gunel. And it's based on this idea that we train a number of original models, and then we train a number of mutants. So we create a number of instances of both the original and mutated model. We evaluate them on the test set, and then we compare these two sets of performance metric, whether it's accuracy or loss. And then we say that the mutant is killed if the test set can successfully detect a statistically significant difference between these two sets of models. So we get, for example, accuracies from the original, we get from mutated, we give them to statistical tests, and if it says that that these two sets are statistically they're different and it's statistically significant, we say that our test set was able to kill this mutant. Then we have also the mutation score. In traditional software, the mutation score is usually is a ratio of the number of the killed mutants to the total number of mutants. Here we had to adapt this a bit, and what we propose is so again, based on the example of remove portion of training data operator, if we say that our test set can kill the mutants with the percentage of deleted data from 25 to 99, and our training set, which is should be more sensitive because the model was trained on it, can actually detect up to 5% of deletion of the training data. We find the ratio of these ranges, and we say that this is the mutation score of this test set for this operator. And if we want to find a general, like the overall mutation score of the test set across all the operators that we have, we just find an average of the mutation scores for individual operators. Then once we have built our framework, we developed the tool and the operators, we needed to evaluate them. So for this, we collected a benchmark of different subjects, 5 of them, and we wanted the subjects to cover different areas of applications. So we have a subject based on MNIST dataset, which is for handwritten digit classification. Then we had the subject for eye gaze direction detection based on the Unity Eye simulator. Then we had the speaker recognition system, which based on the audio recording can predict who is the speaker. Then we have a movie recommendation system, and finally the self-driving car for the Udacity challenge. So here we can see the numbers of the mutation operators from DeepCrime that were applicable to each of the subjects. And here the number of created configurations when using different parameters. So in general, we trained 100 original models and 13,400 mutants to do our evaluation. And we had a set of research questions. So first of all, we wanted to know what are the interesting mutation operators. So as I explained before, we wanted to know which mutation operators produce mutants that are killable, but are not too trivial to kill, because if a mutant can be killed by any test input, it's probably cannot say much about the quality of different sets or different test inputs. And the same about when it's just not killable at all. So to do so, to judge it, we have evaluated our operators from two sides. So first of all, we check the killability. And by killability, we mean that if there exists at least one killable configuration of this mutation operator, we can say that basically this mutation operator is killable. And then we also checked from the other extreme, we check the triviality. So if too many inputs are able to kill the mutant, it's trivial and it's not interesting. So anything in between would be of interest and of a use for us. Then we wanted to know what mutation operators produce redundant mutants, which means that maybe we produce too many mutants, and producing each mutant requires some time and resources, and maybe we can have a smaller set that will be enough to judge the quality of the test set with the same accuracy, let's say, reliability. And here we say that a mutant is redundant with regards to another mutant if the killing set of the first mutant subsumes the one of the second. So if too many mutants kill the mutant, too many inputs kill the mutant, and this set of inputs subsumes the killing set of other mutants, is probably redundant and not very interesting for us. And finally, we wanted to compare our pre-training mutation operators with those available, which, if you remember, I described before, those that train the model and then just randomly tweak the weights of the model. So we wanted to know whether we are actually better in judging the quality of the test suite. So to do so, we measured the sensitivity of the operators. So we measured the reaction of the mutation score of both sets, different types of the operators to the quality of the test set. For this, we constructed for each subject 2 test sets, so a stronger one and a weaker one. And we see the mutation score for each set of the operators shows better the difference between these 2 test sets. So some results showed us that indeed our mutation operators are killable and non-trivial. We found only one mutation operator from those that we proposed that create mutants redundant for each of the subjects that we evaluated on. And we showed that our pre-training mutation operators are more sensitive than the post-training ones. And yeah, that's it. So in summary, today I told you about our framework for mutation testing for deep learning systems and how we proposed the DL-specific mutation operators. Then we adopted new notions of mutation killing and mutation score for deep learning. And finally, we showed that our approach outperforms the existing literature. And our tool and the paper was published in ISTA previous year. The artifact and the tool is available. We also made available all of the mutants that we generated. It was a bit painful, but we did it. So yeah, I think now it's time for questions.